So let's talk about cross-validation. This is used when you have a limited amount of data. So for example, let's say you have 300 training instances. Actually, it's 300 instances that you can use for training or validation. It's up to you. And so you might decide, I'm going to go ahead and break up part of it to be the validation. Okay, so maybe this is size 30. Sorry, let's make it 60, size 60. The problem you have here is twofold. One problem you have is that now you no longer have 300 instances to train on. You only have 240 instances. So it's a very small amount of data. The second problem you have is that the size of your validation set, 60, is not really that large. And so you have a lot of variance in whatever loss you get from that, right? If you happen to pick 60 here, these might happen to be easier training examples than if you chose 60 here or 60 here or some other set of 60, right? And so the measure itself has a lot of variability. When we get into larger data sets, like let's say instead of 300, it's 300,000, and our validation data set is 60,000, that number 60,000 is so big, right? Law of large numbers leads us to imagine that it didn't really matter which 60,000 we got, it's fairly representative. But 60 out of 300, or you can imagine if we took it down by a factor of 10 to 6 out of 30, which 6 those were would matter a great deal. So what we're going to look at is something called Kfold cross-validation. And in this particular example, what we're going to do is we're going to say that K, 5. We're going to do 5-fold validation. How are we going to do this? Well, what we're going to do is we're going to go ahead and go through from I equals 0 to, we'll just say K minus 1. And what are we going to do? Well, we're going to say the validation is going to be equal to the instances, and I'm just using kind of some Python notation here, slicing. So it's going to be using the instances from, let's say that 300 instance. So this is n, and we're going to call this, well, actually we can just do this. So we will do, we want to get, in this case, from 0 to 59. So we're going to go from I times n over k to I plus 1 times n over k. So the first time through the loop, this is going to get the instances from 0 to n, which is 300 over k, which is 5, so to 60. So we're going to get 0 to 59 for the validation. And then what do we do? Then we're going to say the training is equal to the remainder, the remaining instances. We train a model from scratch. We measure the validation loss and accuracy. And we save. So at the end of this loop, what do we have? We have n over k measures of validation loss and validation accuracy. And we may have some variance in here, but if we average these together, we can get a good estimate of the true validation loss and true validation accuracy. So again, just to make clear what are we doing here. The first time through the loop, this is the validation set, this is the training set. So this is I equals 0. When I equals 1, this is the validation set. And so that's the validation set. We're using the remainder of the training data, so that's here, plus here is the training data. So whenever we're training, the validation is completely separate from the training. We're training from scratch, and so the model has never seen the validation data. Right? The previous trained model did. This trained model, we're resetting everything back to scratch, and it doesn't get to see this validation model as it's training. And then we only use this validation data to go ahead and measure that loss at the end. And then we go ahead and do this validation, and final this validation for our final 5-fold cross-validation. So the claim is that this is going to give us a good estimate of the validation loss and accuracy. The problem is, what are we going to actually use for prediction? Okay, we have, well, I guess what we should really do is probably save each of these models. So we now have 5 models, M0 through M4, let's say, and we can choose what we want to do with those models. We could say, why don't we just choose the one with the lowest loss? But remember, there are 2 ways we could get this lowest loss, right? One way we get this lowest loss is because of the way we train the data. The other way we can get the lower loss is just because we happen to choose a lucky validation set. And so that's probably not a good idea to do. Instead, what we could do is use an ensemble. So we have our 5 modules, we have our 5 trained models, M1, or I called them M0, through M4. When we have an X coming in, we feed it to each of the models. From the model, we get a Y hat, probably a different Y hat, at least slightly, for each one. So we have Y hat 0 all the way to Y hat 4. And what we can now do is average those to get our final Y hat. So that works reasonably well. It has a few disadvantages though. One disadvantage is neural networks, normally our models are kind of large and also somewhat slow to infer. So it may be somewhat slow to do this inference. In other types of machine learning models, that's not the case. Random forests are very small to store, and they're also very fast to do inference on. We could afford to have K different models and use each of those models for inference. We do have a second approach. So the second approach is retrain from scratch using the same hyperparameters we used here. So the same hyperparameters that we used here, and we may have gone through and done this process many times, right? We may have run through this, said, this average validation loss is not good enough. Let's make some tweaks to the architecture, add some regularization, do something else, run through it again, run through it again, run through it again. Okay, we're happy with validation loss. Now we go ahead and freeze, save all those hyperparameters that we're going to use, right? Number of epochs, amount of dropout, any sort of data augmentation, all that sort of thing. Okay, we use the same hyperparameters. What data do we train on? And this is the key. We go ahead and train on all n instances. So before we were reserving n over k for each one of these. Now we just go ahead and say, well, we're not actually going to do, we don't need to do any validation on this because of the fact we know our estimate of the validation. So go ahead and retrain from scratch. We're actually training with more data, so we wouldn't expect to be overfitting, right? If we weren't overfitting before, adding more data certainly isn't going to make us overfit. That is what we do. How do we go ahead and then determine what our actual accuracy is going to be when we go out in the real world? We will use our holdback test set for that. But this is our best estimate of it at this point. So that is our best estimate. It's possible we were overfitting on the validation if we ran this many, many, many times. That is Kfold cross-validation. One thing about the Kfold cross-validation that's nice is it's easily parallelizable. That is, if you just take K machines, you can go ahead and train K models in parallel, measure the validation loss and accuracy, and then come up with that average at the end.